Hi, this is Felix, and today we are going to talk about MRI scanning. Perhaps you have had an MRI scan done, or you know someone who has had one done. In either case, you know you've gotten inside of a large magnet. Well, exactly what is this magnet for? We will go over that in a minute. So the first word starts with an M, and that stands for magnetic. The second word is for resonance, and we will go over that in a minute as well. The third word is imaging, which is the entire point of an MRI. The doctor can see what is going on inside your body with an MRI scanner. Now, MRI is quite a bit different from X-ray. In X-ray, we've got an X-ray tube that generates high-energy photons in the X-ray range. These basically create a shadow of whatever is in the field. We don't want the photons to be too strong or too weak. We want them to be just the right strength to see what is going on inside your body. MRI is quite a bit different. Now, the way we image with MRI, we are looking at a very tiny element inside of your body. So what is the most common element inside of your body? Well, it is a molecule, and that molecule would be water. Good old H2O. We are told that your body is comprised mostly of water. So the most common element in your body is hydrogen. This hydrogen is bound up with oxygen to form our water molecules. So it is the most basic nuclear element in your body, comprised of one proton surrounded by an electron, the proton with a positive charge and the electron with a negative charge in a shell around the proton. So how is it we image? Well, the first thing we have is our magnetic field. In the magnetic field, we find that the protons will line themselves up. Well, why is this? It is because of the charge of the protons. They line themselves up because they have a charge and therefore a magnetic field. Normally, the protons in your body are in all different directions, and basically an infinite number of directions given the vast quantity of protons in your body. These can be in so many different directions that if we were try to impart signal to these protons, they would simply cancel out. That wouldn't do us any good. An interesting thing happens inside the magnet. Besides lining themselves up with the field, these protons can have a wobble. Now again, we said that the magnetic field keeps them aligned. But if you've noticed with a gyroscope or a top, for instance, they might have a little bit of a wobble, especially with a gyroscope. This wobble about an axis here is called precession. The tip of the gyroscope will wobble in a circle. Now, in the case of a proton, we have to impart energy to them to get them to wobble because the magnetic field is holding them in place. Now, this can also be used to extract information out of the protons. Now, how is it we do this? Well, we find that this rotation, this precession about an axis here, happens at a certain frequency within the magnet. This frequency depends upon the element we're scanning and the magnetic field. Typically, a lot of magnets are at 1.5 Tesla, and this relates to the frequency of precession of 63.86 megahertz. So this is basically a common frequency in the radio band. So what do we use? We use an RF transmitter. RF standing for radio frequency. You'll see these transmitters around town, and this is what we use to receive over-the-air broadcasts. Well, the neat thing happens, so once we place this RF energy into the magnet, we find that the protons, which are normally upright, want to tip over. The energy imparted causes them to tip. They're still spinning, they're still precessing. This tip is happening in a circle. But this imparts energy. We're putting the energy, RF energy, into the system. And as long as we apply this energy, the protons will stay tipped over. Now, how is it then that we receive the energy from these protons? Well, it just so happens that when we turn off the RF transmitter, the protons want to snap back to their home position. And in doing so, they give off RF energy. Same type of RF energy we just imparted to them. Again, this is at 63.86 megahertz, so we can measure the signal. Now, one more thing I'd like to talk about here is that within the magnet, all of your protons are lined up. But if we simply add signal, we would excite all of the protons. So what do? Well, we add fluctuating or changing magnetic fields, much weaker than the main field, but one of them in the line of the same direction of the main magnetic field, but the other two on the other two axes. And the purpose of this is so that we can change the field so it's slightly weaker on one side and slightly greater on the other side. Again, the precession depends on this resonance. So if we only want to image right in the center of the magnet, we can add this field, this difference in field strength, so that the protons along one side and the other side do not resonate. That allows us to select which protons in space we are looking at. So these changing magnetic fields in all three axes can be used to discern between the information, say, at one point and another inside the magnet in similar fashion to what we have shown along the main field. These magnetic fields, by the way, are called gradients because they actually form a gradient along the main field, lesser on one side and stronger on the other side. But this field is actually linear. This is a very complex process, but by controlling the gradient fields and the corresponding RF transmit signal, we can create differences in the received signal depending upon where in space that signal is coming from. These differences can be plotted in the phase and frequency direction. So we have seen that inside of your body, by using magnetic fields and RF energy, we can impart information or signal into your body and receive that signal in various forms. Now, typically this information is imparted to, or it's plotted on what we call K-space. In K-space, you're just getting the signals. This is in a very complex form. Typically, the signal is stronger in the middle and gets weaker as it goes out, often forming like a star pattern. This is called K-space. Now, this wouldn't do much good for a radiologist. Looking at this star pattern wouldn't help him too much discerning what is going on inside of your body. So, we need to decode this information. And to do that, we use a mathematical concept called a fast Fourier transform. Now, don't be too concerned about that. If you want to think of it as simply a black box, that is just fine, or a decoder for that matter. So let's put decode here. You can liken what's happening in a Fourier transform to say what's happening with your home stereo speaker. In a home stereo speaker, you have frequencies of various wavelengths. You've got your woofers, tweeters, and mid-range, high, low, and medium frequencies. Now, if we convert that to a different form of plot, we can look at that on a frequency spectrum. So this same type of analysis, the same change is called the Fourier transform. It's what's going on inside, except far more complex than in your stereo. What happens then is the image comes out the other end of the Fourier transform. This is where the radiologist will look inside your body and see what's going on. So there is just a myriad of ways that can be utilized to determine differences between one tissue in your body and another. I'll just go over one here real quickly, and that is how long it takes different tissues to lose their signal. One may lose its signal rather slowly and one rather rapidly. And you can see by the time this one has lost all of its signal, this one still is quite bright. So we can see these differences on the images, and this is what the radiologist sees. So that's just one of very many ways. So thank you for joining me on this brief description of MRI. I hope this was helpful. If so, please like the video. Until next time, this is Felix. Thank you very much for joining me.